We'll now look at some additional examples for equivalent statements. Our first example asks us to determine which of the following statements are logically equivalent to this statement. It is not true that the tire is both out of balance and flat. So let's begin by assigning some letters to the two statements that we have. Let's use P and Q. So I'm going to let P be the fact that the tire is out of balance. And let's let Q be that the tire is flat. So with that in mind, let's transform our statement into a symbolic expression. So to say that it is not true, we're going to use the negation symbol. That the tire is both out of balance, so that is P, and we'll use our symbol for and, the tire is flat, that is Q. So let's look at part A. Part A says if the tire is not flat, then the tire is not out of balance. So what is that asking us to prove? If the tire is not flat, so not flat would be a negation of Q with an arrow. This says if the tire is not flat, then the tire is not out of balance. So not out of balance would be the negation of P. Now, in order to determine if these two statements are logically equivalent, what we need to do is set up a truth table for this one and also for this one, and see if the truth tables produce the same answers. So let's do that. We'll begin with the first one. I am going to do a column for the P and a column for the Q. Remember that in the P column we'll have 2 true values and 2 false values. And in the Q column we'll alternate true, false. And then we will do the negation, and in parentheses, P and Q. So let's work inside the parenthesis first. Let's look at what happens if we have P and Q. We know that if P is true and Q is true, then the result is also true. We know that if P is true and Q is false, the result will be false. False and true, the result will be false. False and false, the result will be false. Now, we need to find the negation of those values. So we're just going to take the opposites. So starting with the true, this will become a false. The last 3 are false values. They will now become true values. So this column represents the answer for our first truth table. Let's now construct a truth table for this expression. So again, I'm going to start by doing a P column and a Q column. And then we'll extend and we'll calculate the negation of Q, implying the negation of P. So let's go ahead and fill in our columns for the negations. For the negation of Q, we're going to do the opposite of these values. So we'll have false, true, false, true. And for the negation of P, we'll do the opposite of these values. So we'll have false, false, true, true. And then let's do the conditional in the middle. If Q, the negation of Q is false, implying the negation of P is false, then that is a true statement. If the first one is true and the second one is false, then the condition is false. If the first one is false and the second one is true, the condition is true. And if the first one is true and the second one is true, the condition is also true. So this is our answer for our second truth table. Now the question asks us if these are logically equivalent. Remember, they're logically equivalent if both statements have exactly the same values. And we can see that these two do not. We start with an F and we have a T over here. So right there I know that they are not logically equivalent. All right, so let's go ahead and look at a part B to this same problem. Part B said the tire is not out of balance or the tire is not flat. So what does that mean using our symbols? Not out of balance would be the negation of P. We'll use the or symbol. And the tire is not flat would be the negation of Q. So let's set up a truth table for this one. Again, we'll start with our same four values for the P, and then we'll alternate for the Q. We'll do the negation of P, we'll do the or, and the negation of Q. All right, so for the negation of P, we're going to do the opposite of the P values. So we'll have false, false, true, true. For the negation of Q, we'll do the opposite of the Q values. So false, true, false, true. And then we'll do an or in between. So if the P value is false or the Q value is false, we have a false. If the negation of P is false, the negation of Q is true, the answer is true. A true and a false make a true, and two trues make a true. So this is the answer for part B. Now let's go back and let's compare that to the original truth table. So note here we have false, true, true, true. We're comparing it right here, false, true, true, true. And we can see that those two are exactly the same, which means that yes, these two statements are logically equivalent. So remember, in your truth table, if you have two statements that are logically equivalent, they must have exactly the same truth values in the truth table. Our next example uses De Morgan's laws of logic. It says to write a statement that is logically equivalent to, it is not true that tomatoes are poisonous or eating peppers cures the common cold. So let's assign letters to these two events. Let's let P be that tomatoes are poisonous. And we're going to let Q be that eating peppers cures the common cold. And then let's take our statement and transform it into a symbolic statement. It is not true, so that gives me a negation that tomatoes are poisonous, that's the P, or, we use the symbol for or, eating peppers cures the common cold, that's the Q. Now, let's remember what De Morgan's laws of logic actually say. We have a statement for De Morgan's laws of logic. I'm going to write it right up here. That says this. It says the negation of P or Q is equivalent to the negation of P and the negation of Q. So what that tells me is that this that we've come up with here will be equivalent to the negation of P and the negation of Q. And so now what we need to do is we need to translate that back into words. So the negation of P would be that tomatoes are not poisonous, we have the and symbol in the middle, and then we have the negation of Q. So that would be that eating peppers does not cure the common cold. And so that is our statement that is logically equivalent. We're going to do one more of these examples. Write a statement that is logically equivalent to, we cannot go to the fireworks, but we can go to the ice cream shop. Again, we're going to assign some letters. We're going to let P equal, we can go to fireworks. And we're going to let Q equal, we can go to the ice cream shop. And let's take our statement and let's transform it into a symbolic statement. It begins with, we cannot go to the fireworks, which is a negation of P. Remember that the but is another way of talking about and. And so we'll use the symbol for and. We can go to the ice cream shop, which is Q. Now again, let's look back at De Morgan's laws. And note that we have a statement that says the negation of P and Q is logically equivalent to the negation of P or the negation of Q. And so let's take that and let's rewrite this for our problem. And now let's take it and transform it into words. So the negation on the outside of the parenthesis means it is false. That P says we can go to the fireworks. Or, and the negation of Q is we cannot go to the ice cream shop. And so now we have a statement that is logically equivalent to our original statement.